Thank you for coming, everybody. I'm glad to not be the session right before lunch. Less glad to be competing with Kyle and his Jepson talk. That seems pretty unfair, but hopefully we'll all have a good time. So I'm here to talk about load testing. We'll discuss very briefly why you should listen to me, why I know something about this. I think it's important as well that we talk about why you would even bother doing load testing. I think there are a lot of things that we do as developers that we probably don't need to do, or we do because they're fun, not because they're necessary. And then let's get into the depths of how you design a proper load test, how you design and think about performance experiments, how you run these things, and how you analyze the outcome. In my current role, I'm CEO at Skipjack. We do machine learning-driven performance optimization, so we do a lot of load tests, a lot of performance tweaking, a lot of configuration editing, all driven by machine learning models. So it's very close to my heart, this topic of running a really high-quality performance, a load test, because without that, all of our results are kind of useless. Prior to that, in a very much past life, I was also co-founder at SpringSource, did a whole bunch of Java stuff on the Spring framework, but I don't really do much coding in Java anymore. So let's think about why we might bother at all about doing performance testing. We can kind of say, you know what, we all care about systems being fast, and there's like professional pride in wanting to make sure that you have a fast system. No one wants their friends to use a system that you've built and it'd be really slow and you kind of look a bit foolish. But why should your business care? What is it about performance that has a business advantage? And the reality is that fast systems are systems that have high revenue. At AWS reInvent last year, the CTO of Trainline, the train ticket booking app, got up on stage and said that he reduced his latency of the Trainline app by 300 milliseconds and made an extra $10 million a year. So that's definitely worth putting some time into, right? I mean, how much money do you have to spend before that becomes wasted effort? It's worth spending $1 million to make another $10 million. And that's $10 million he'll make next year, and the year after, and the year after. And there's this huge body of research now that says time is money, performance is money. That's actually Benjamin Franklin, and he is actually the person who apparently originally said that. I didn't believe it at first, but it's on Wikipedia, so it must be true. We all instinctively know that faster is better service. We've all used slow websites. We've all become exasperated when trying to load a page and just can't bother anymore. I know I do pretty much all the time. But also, we kind of don't necessarily intrinsically understand, but I think if you're in this business, you kind of get it. The better service means improved conversion. If you're Amazon, you want people to check out. You want people to add more things to their basket. If adding to the basket is slow, if checking out is slow, people will give up, people stop. And there's just this huge body of research that shows this. So there are some practical examples, people who are doing it themselves and analyzing their data. So Shopzilla, 5-second latency reduction, 7 to 12% improvement in conversion. It's pretty good. For someone the size of Shopzilla, that's probably a lot of money. Walmart, they're pretty big. Every 1 second latency reduction, 2% increased conversion, which must be tens of millions for Walmart. Like, the amount of time people spend buying on Walmart, that's incredible. Mozilla, though, was an interesting one because they don't really sell anything, but they showed that for other important things you might build a system for, in this case, downloads of Firefox, that performance also matters. So they reduced the latency, average latency, not a great measure, but they reduced the average latency of the download page for Firefox and got 15.5% increased conversion to download, which is pretty cool, given they're trying to fight this battle to win out over Chrome. So I'm really keen on this idea of trying to explain to people how much money they can make by making their system faster. I have some friends who are in a very conversion-heavy business. They're in consumer finance, and they are doing this big marketing effort at the moment. They're trying to find ways to extract ever more out of the visitors they get to their site. And they're going to invest tens of thousands of pounds into a marketing effort. The reality is, though, that money would be better spent by them on improving the performance of their system because it's not yet at the cutting edge of where you can be. And actually, in the recent State of Online Retail Performance report, it finds that over sort of 2.5 seconds of page load time, you're well outside the peak for conversions. So think about that. If you've got web pages that are taking more than 2.5 seconds to load, you're leaving conversions on the table, you're leaving revenue on the table. But the other way of thinking about it is in reverse. Like, yes, we can make our performance better, we can make more money, but what happens as performance gets worse? What happens if we're putting out new builds, we're making changes to the system, we're maybe tweaking the configuration of our garbage collector or Linux or something, but things are getting worse? What can happen? Well, revenue goes in the opposite direction. This isn't a unidirectional thing. It is actually possible as a developer to make a code change, put it into production, and stop people from buying stuff. So a good way of thinking about this is that a slower system's kind of like a partial outage. Think about it. If you've ever been to a web page that took like 10 seconds to load, is that really any different than a web page that won't load at all, or a web page that takes 30 seconds to load? You know, it's not all that different. The Track Research guys did this survey among their customers, and they found out that 1 hour of downtime on average costs organizations about $21,000 of revenue, which is pretty bad. Ooh. And 1 hour of slowdown costs about $4,400, which is also pretty bad. But the kicker is this. Slowdowns are 10 times more likely than outages are. You're way more likely during the day to encounter a slowdown, like a partial outage of your system, than you are to see a complete outage. And in that sense, we think, well, slowdowns are actually costing twice as much revenue as outages are. So we should be putting a lot of effort into this. We should be thinking about it. And it really all starts with testing. You need to be doing some performance tests, thinking about what those results mean for your organization, and then having a plan for remedial action as needed. If you find your system is too slow, you need to fix it. You need to make it faster. If you find it's getting slower, you probably need to do something about that. And if you're looking for ways to optimize conversion, then you need to put some effort into optimizing your system. But without a way of testing your performance, you're going to be kind of lost. If you take nothing else away from this talk, this is the most important thing, that load testing is a process. It's not a one-off thing. When we're doing system-wide tests, it's not sufficient to kind of create some test scripts, throw some load at a system, get some numbers out, and sit back and go, I'm done. There's a whole process you go through by maybe you need to run some more tests. You definitely need to analyze the results. You need to understand what those results tell you. Maybe they tell you the load you generated wasn't even remotely sufficient to push the system to its maximum capacity. Maybe you hugely overshot the system's maximum capacity, in which case the results are completely questionable. It's a process. But it's also a process in another dimension. It's a continuous process. So if you think about each load test as being this kind of iterative process, you can imagine like load testing as a whole to be a continuous process. Every new build, really, that you're putting into production should be tested. That might be impractical, so maybe you're doing it every day or every week or every month. But there should be a continuous means by which you're testing the performance of the code you're putting into production and then doing something about any kind of remediations. Or if you're trying to do an optimization, if you're trying to make your page load 200 milliseconds faster because you want to find a few $100,000 of revenue, then that's a process too. You're not going to do it all in one go. I like to think about it as this. I start with a purpose. And it's astounding to me that many people don't start out with a reason to load test. It's kind of like a reason in itself. I'm doing a load test. Great, but why? What's your point? Are you trying to figure out, like, do you actually not know how your system performs? A lot of people are there. Are you doing it because you want to get a benchmark for optimization? Or are you doing it because all of a sudden conversions are dropped? Knowing what you're trying to answer, like what are you trying to find out, is critical to how you design your test. Then you've got to design your test. This is why I hate the word test for performance testing. This is not like JUnit. It doesn't pass or fail. It's not like, yep, the system is fast. Oh, yes, it's super fast. These are not binary outcomes. There's a qualitative aspect to this. You have to evaluate the results in the context of your business. And therefore, the design is critical. You need to spend time thinking about, how am I going to acquire the data about how my system performs so that I can answer the questions that I have. Just blithely writing a performance test script doesn't help here. You obviously have to run the test. I think a lot of people put more effort into that than they do into the other parts of this. And I think really that's kind of wasted effort if you haven't got the design right and you haven't kind of got a clear purpose set in your mind. It's definitely worth putting time into running the tests, for sure, but don't invest all your time there. Then likewise, I see analysis just push to the end. Like, we've got some data now, let's just find out what our average latency is and be done with it. And if it's a good number, let's definitely stick with it. If it's a bad number, the test was clearly wrong, so the system performs just fine. And eventually there's some glory, like something good happens. But it doesn't just happen by being passive, you need to be active in this whole process. One thing that's nice about this is it's not kind of wasted effort. Once you've designed a load test, you can kind of reuse it again and again and again. With our customers, we find that we'll build a test model for them. We can run, I don't know, a month's worth maybe of load tests for them. Then we want to refresh that model, see what's changing in their environment, keep refreshing it. You're getting more than one test off your design effort. How many? Really depends on what your system is. If your audience size is changing like day on day, maybe you're an early stage growth company, you're ramping up hugely, the audience makeup's going to change, so how you test your system's going to have to change as well. You must revisit your design as the landscape changes. It's so common to see customers who say, oh yeah, we've got a JMeter plan. And you look in GitHub, last change was like 2 years ago. You just think, how accurate is that compared to what you're doing right now? Probably most of those endpoints don't exist anymore, or they're just kind of completely irrelevant, and the makeup of the customers that you're simulating doesn't exist anymore. You need to revisit that on a regular basis. I'm going to go out on a limb and say most people here are probably pretty good at running load tests. It doesn't actually require a ton of expertise to design a load test. It's pretty easy to see when you've got it wrong as well. I think like if you're putting a bit of thought into it, you can kind of see what's gone wrong. But not a lot of people who I've encountered have put much thought into how they design those tests. Like what are they actually testing? So it's really important to figure out what's the best way I can run this test, and that's where the design happens. I mentioned this already. The term test is kind of strange. I prefer to think about it as an experiment. You've got some hypothesis about your system or some question you want to answer, and you're going to run one or more experiments to try and prove that hypothesis or answer that question. Maybe you want to find out, where does my system fall over? How many concurrent users can I handle before everything goes terribly bad? That's a really good question. Maybe what you're interested in is, I've got this build here, and I've tweaked the GC settings in this build here. How do they compare? Is this one better or worse? It's a traditional hypothesis testing problem. It helps to think about it as being an experiment rather than a test. You want to define the purpose, so we said that already. If you do this right, you can pretty much get all the data you need to answer a whole swath of questions, which is quite nice. And then critically in step 2, and you want to put time into this, you want to construct a high-quality test plan. If you generate a whole bunch of test traffic that bears no resemblance to your production traffic, you may as well not bother because the results are completely invalid. And I got some thoughts on that, and I'll give you some ideas about how that might work. So let's talk about the purpose. As I said before, for a lot of people, the purpose is we need to do a load test. Recently spoke with an investment bank who doing some migration to cloud, realized kind of at the last minute they need to do a load test, but it's a tick box exercise. The compliance department or some department won't release the build into cloud until the load test is done. It's not clear to me that the outcome of the load test could change whether or not it goes into the cloud. It's just a tick box feature. And it seems like that's the case for a lot of people. But let's think about what we could really try to do with a decent load test. Well, first thing is we could say, what kind of latencies do I see when I've got 10, 50, 100, 200 concurrent users? And I'm using the term concurrent users here rather than just saying like, X requests per second, because it really helps to think about, especially system-wide performance like this, in terms of what's happening when real users are in the system. If all you do is generate like 1,000 requests a second hitting the home page of your website, that's not really all that accurate. In real world, some people are hitting the home page, some people are visiting your Contact Us page, some people are visiting your checkout page, and that's affecting the back-end system in different ways. Different queries are being executed, different caches are being filled and expired, and it's really important that the makeup of your test traffic exercises the system in the right way. So I like to think about the load levels that we're generating in terms of users rather than requests. Likewise, I like to think, how many concurrent users can I handle before all of a sudden my latency exceeds some bound? If we take the data from the online retail performance report, 2.7 seconds is kind of where we want to push to for peak conversions. So we might say, how many concurrent users can I handle before 95th, 99th percentile latencies exceed that? And we can find that out in a test. And a really important one for most people is, how many concurrent users can I handle before my system is saturated? And saturation is a really important point, and a lot of people mean different things by this, and there are a whole bunch of ways of measuring it. I prefer to measure it in the simplest kind of externally visible way I can possibly imagine, which is to say, how far does saturation is the point when all of a sudden latencies just start growing unbounded. And you can imagine this as being like everything in the system could be fine apart from one resource, and that resource could be the CPU or memory usage, or the GC is kicking in all the time, or there's some lock in Java somewhere. But that's causing the bottleneck, and I can no longer handle any more concurrent users, so all the new ones are just backing up in this queue somewhere, and latency is just growing unbounded, 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 unbounded. And I don't know if Martin will mention this tomorrow in his talk, but he does in many of his other talks. This is just simple queuing theory. At a certain level of utilization, the kind of wait time for a system, in any kind of queue-based system, and all of our systems are queue-based systems at some level, will just grow unbounded. And that's when things get messy, and then you probably want to provision for just under that, or just for some buffer under that saturation level. I don't think it's useful to try and capture saturation in terms of resource usage, because there could be some resource usage you're not measuring. It's not like saying, oh, well, CPU usage is only 80%, so everything must be fine. Because there could be some other resource you're not measuring, or there could be some lock in Java that's causing arbitrary things. Like one thing we see time and time and time again in optimizing configurations for customers is that they provision like 5 connections in the connection pool. So people end up backing up behind the connection pool. CPU usage is low, memory usage is low, can't go any further, you should only do 5 concurrent queries at a time. So you need to do it, I think, from an external observable point. Should talk a little bit about measuring latency at this point. This is new batteries, and it's still going wrong. This is where things go a bit crazy. Average latency is almost useless as a metric, despite the fact that you'll see it in most major monitoring tools. And the issue with average latency is it doesn't tell you anything about really what most of your customers are seeing, or the shape of your distribution, or anything. A couple of key things to remember here is that most latency distributions are not bell-curved shaped. They don't look like a normal thing, so you can't say, oh, well, the average is clearly the central tendency here, so some are a little bit worse, some are a little bit better. You can't say that. You also have to bear in mind that most clients are making multiple requests to your system. So as they do that, the chance of them seeing something worse than the average gets bigger, 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 bigger. So a really useful metric to think about actually is what's the worst observed latency per customer, and tracking that's very interesting because you can correlate that with bounce rates and drop-off and so on and so forth. But if you're using standard measurement tools like New Relic or Prometheus, or we're using InfluxDB and Grafana, capturing later percentiles is really handy. 90th, 95th, 99th, 99.9th, those are really useful things. Max is always very useful, although in a test, it's not great because it can never be corrected down by more samples. If you imagine, like, if I do 1,000 samples and my 99th is here, then I do another 1,000, it could shift down or up, but max can never shift down. So you may have had one anomaly that's nothing to do with the real behavior of the system. So it kind of helps to run the test a few times, I think, in that instance, to get a good view. But my preference is to consider the whole distribution. There was a great tweet recently. Someone showed 5 summary statistics, mean, standard deviation, min and max for data sets, and then showed that they basically, with the same summary, for 12 completely different data sets. They just looked completely different, but they had the same summary statistics. So the most valuable thing you can do is look at your distribution of latencies as a whole. Histogram, all different kinds of plots, but you need to visualize it and understand what that means. You might see bunches of peaks, which maybe are different request types if you're looking at latency as a big thing, or if you're looking at one request type. It might be requests that are served from cache, requests that are not served from cache. It might be, some customers have 50,000 addresses in their address book and some have 2, so the queries take different time. It's really useful to visualize the whole distribution of latency. I did some tests for this slide deck. This was the quantile plot, roughly, of what the latencies look like. So you can see up to even 99.7, it's fairly low. It's 1.5 seconds maybe. But then past that, it starts to creep up. And then past 99.8, it just gets crazy, with the max being way up here. If I did a lot more samples, obviously I'll have a lot more detail in the tail there. But this is what people see in the real world. These tail latencies matter. If you make 42 requests to a website, your chance of seeing something worse than the 95th percentile latency is almost certain. That's kind of interesting. And Google showed that the average number of requests made when a web page is loaded is about 42, which is great, isn't it, that it's 42? But you need to consider these tail latencies much more than you need to consider your average latency. Performance testing is expensive, both in time and typically in cost. You need to fire up machines, test environments, so on and so forth. So it can be worthwhile trying to figure out, can I answer multiple questions at once? Can I fire up a test system, have it in a resettable format so I can, after every test, reset it? And can I gather so much data in one go that I can answer a whole bunch of questions? And the best way I found to do that is to think about testing as a series of experiments where you try to figure out how your system behaves as you ramp up the load when you plot it against latency. What's that curve as I scale up? And if we had an ideal world, we'd get linear scalability. If we generated 10 virtual users, we'd get 10 virtual users worth of throughput. If we generated 20, we'd get 20 virtual users worth of throughput, so on up to 100, 1,000, and so on and so forth. But we won't see that. At best, we'll see something like this, where we kind of reach a plateau. So you can see here, it sort of scales linearly roughly early on, but then it starts to plateau. There are many reasons for this. Most likely, though, what you'll see is you'll reach some point here, and then performance will start to degrade, actually. There are kind of crosstalk penalties in many systems. Maybe you've got database transactions where different servers have to agree. Maybe you've got multiple processors where the memory subsystem has to have this kind of crosstalk overhead. There's a way of modeling this, and we're going to get to that a little bit earlier on, but it's worthwhile thinking that understanding this curve tells you a lot about your system. So if we think about that, okay, what we want to do is try 10 virtual users, 20 virtual users, 40, 80, so on and so forth. How do we go about doing that? Well, it helps to build a test plan that's quite descriptive of our user audience rather than prescriptive. And let's see what I mean by that. Everyone at work hates the fact that one day I turned up to work and said, we need to stop using the word test plan. We need to start using the word test model. Because a plan is a silly idea, and a model is much better. And the reason is this, and I stand by this, test plans are prescriptive. They say, do this, hit this web page, hit this endpoint, wait for 2 seconds, hit this endpoint, wait for 2 seconds, hit this endpoint, wait for 2 seconds, and then they play that 50 times, because each customer obviously does the same thing in your system, as you well know. It's about as inaccurate as you can possibly imagine. A model, in my mind, is something that describes your audience. It says, these are how people enter my system, and then when they're in there, these are the kind of transactions they do, and these are the rates that they do those transactions, and this is kind of how they progress through the system. And it has this kind of probabilistic nature. You can build a model from your traffic that says, I know that the entry point is 10% likely to be this, 20% likely to be this, 70% likely to be this, that the next on-bound traction is likely to be this, and so on and so forth. You can build this model, but you have to build it from real data. So imagine a test plan like this. This is for our very enterprisey website. We've got many pages. Most people come to our homepage first. People check out our offices. We just moved. People look for jobs, and then people hit the team page, check out who's who, and then kind of cycles back. And if we were doing this in a traditional way, we'd fire up 50 threads, 100 threads, and we'd run 50 virtual users doing those same set of transactions each time. If we're being advanced, we might actually say, well, people wait in between doing those requests. But if we're not being advanced, what we'll actually do is just keep powering the system. Because we're desperately trying to find what's the maximum request per second. All the while, the traffic we're generating does not even remotely represent what's in production. I hope to have a really good picture for this, but I couldn't get it done. I can't draw. This is where load tests go to die. If you start at this point, everything else you do is pointless. You could have the best load test environment with like really high quality production data that's been backported to test. You could have a big farm of test machines. You could spend like 5 hours running each test. It's all irrelevant because the load is not at all like what's in production. It is worth so much spending the time to get this right. Like, it makes everything else you do so much better. In a descriptive model, I like to think about it this way. When people come into the homepage, and let's assume for now, because it gets messy, people hit the homepage and then 10% of them go onto the offices page, 30% go onto the team page, and 25% go onto the jobs page. That's interesting. And then maybe once they're on the jobs page, 5% of them come back to the homepage. Notice, though, that 10 and 30 and 25 doesn't add to 100, because some people don't go any further. It's a sad fact that some people come to our homepage, and that's where they leave. I blame the marketing people. It's not my fault. But that's what a real model looks like. People don't do the same thing all the time. Each user is different. And you can have these transaction probabilities, if you imagine this as a graph, or kind of more formally, this is kind of a bit like a Markov chain. It's not quite a Markov chain. It's just a bit more general than that. But these probabilities capture how each user is different. But also, it's important that we capture wait times. Because when you come to the homepage, if you're going to go to the jobs page, that link's at the bottom of the page, whereas the team link is at the top of the page. So you're going to wait longer or shorter depending on where you go. Maybe I got that the wrong way around. And interestingly as well, sorry, I want to just jump ahead. These wait times are drawn from a distribution. So most people go wrong by thinking wait times are typically 0. They'll just hit. Well, in the real world, wait times are a thing. People do wait. I'm sure nobody here buys from Amazon by just like clicking all the pages like we're in some kind of sci-fi movie. You actually do have to browse for which USB to 4K HD adapter you want. That took me an hour. Wait times are a thing, but they're also not static. It's not like everyone here waits for 3 seconds. They're drawn from some distribution. If you don't know the distribution, you can use Exponential as a fallback, but it is only a fallback. It's a good approximation of how internet systems behave. If you say 3 seconds is the average, then it's exponentially distributed. It kind of approximates it. But the best way to do it is to figure out how long people actually wait and build your own distribution and simulate that. But that's getting pretty advanced. Probably the biggest departure I'm going to say from traditional practice in this talk is that you should source all of these parameters, all of these wait times, all of these transition probabilities from real data. So I did this, because we have a tool that does this if you're interested. It's a free tool, and we're doing it from Google Analytics data, but also these are all of the data sources we're working on building at the moment. And it taught me so much about my website. First of all, there are pages on there I didn't even know existed. Like, people are hitting these random URLs that I didn't know were there. And my naive model had, 4 transitions. We had 168 distinct pages with something like 250 different transitions between them. So nobody is coding that by hand. And certainly nobody's keeping that up to date as the audience profile changes. So it's really important that you find a production source of data that tells you what your audience looks like and build your test model from that. And if you don't want to do that, we'll do it for you. I gave this talk, a similar talk, in Copenhagen recently, and 50 minutes is not a long time to talk about performance testing. So one of the things I didn't get into too much was how do you, in load tests, handle mutation of data? Because it's really important. Like you look at my model here, it's all GET requests. But actually people do POST requests. They change things, they change state. This is actually a little bit easier than it initially seems if you put a bit of forethought into it. It doesn't quite end up being as hard as you imagine. So the first thing I think is critical is that you want to start ideally from the same point for each test. So if you're running on cloud infrastructure, like maybe AWS with RDS or GCP with their relational database service, you've got the tools immediately to take a snapshot of the database you're testing against, run your performance test, and then restore from that snapshot. So every test starts from the same place. If you can populate that database with data from production, then brilliant. The Uber guys did a talk in San Francisco last year, and the most amazing thing, they have a tool for Cassandra that when they're testing, they read and write to a test database, but if the data doesn't exist in the test database, it transparently populates from production. But all writes stay local to the test database. So it's as if they're testing with the entirety of production there. Now, obviously, for performance testing, this isn't great because that extra overhead of going to get the data from production skews the results. But if you can copy a snapshot from production, maybe even from like a month ago, it's really helpful to start from the right data. If you assume that all the data you need for your test is present in your database, then you're not actually generating real load. Imagine the Amazon use case again. We probably want the product catalog to be around about there, and maybe how many orders there are, maybe in the database already, but new orders will come in. And one of the most useful things you can learn is that it makes sense to assign either from test data sources or generate test data per virtual user. And I've got some examples of what I mean by this in a second, but just randomly generating data makes tying together test plans really, really hard. It makes sense to actually think about how do I generate an identity for a virtual user when the test starts so that someone who's, like this virtual user who's walking through the system has an email address, has some buying preferences, has some contact details, and they're consistent in the data they present to the system throughout. Try to think of them as being like little robots. They have an identity. Critically as well, these mutation workflows modify the transition probabilities. I've got a really good example of what I mean by this. And then the data you assign varies on the workflow as well. So let's see this in graphical form. Imagine I wanted to extend my plan to support sign in and sign up. And already you can see there are two transactions here. One is I could be an existing user signing in which case I've got my email address and I've got my password, or I could be signing up. This is a silly way of doing it, where I just assume, well, it doesn't really matter which way you go. rob@skipjack.com and correct horse battery staple as a password works just fine. In actual fact, what you need to do is very early on decide what's the probability of this person being new or existing, and then choose the transaction as appropriate. So let's recap on that a little bit. It helps to design with a purpose in mind. It helps to think about each user as being different. If you're testing with the same load per user, you're really not doing it right. And probabilistic models are better than prescriptive plans. Please use production data. It just helps so much. There's so much data out there that you've got about your audience, you should be using it. I'm not going to spend as much time on this as you might think, because it's not all that hard. Like running a load test once you've got a good test plan is actually relatively simple. Just a couple of things you need to bear in mind. Make sure your load test environment is high fidelity, so the system you're testing should be as close to production as possible. If you're using cloud infrastructure, that should be easy. You should just be like making a full copy of it. Make sure you provision enough load generation capacity. Rookie error. You've got like 16 servers and you use a laptop to do load testing on. Those results are not good, I'll tell you now. You will kick yourself if you don't do this in advance, but make sure you instrument the system you're testing, because you're going to want data about memory usage and GC behavior and so forth after the fact. If you spot a problem and you've just spent 9 hours doing performance tests and you don't have the data to find the problem, you've got to do those tests again for another 9 hours. So make sure you get good instrumentation. Then you've got to implement the test model for your load generator of choice. It's not as easy as it should be. None of the current open source tools support doing these kind of probabilistic models. I've got an example for the model that I built, and I'll put it on my GitHub. So we're a little bit tight. I've said this already, the closer to production, the better. And where this typically falls down is in stubbing out systems you need. Like maybe you're doing flight booking app and you need something like Navitaire or Sabre or something. There's a really cool open source tool called Hoverfly. If you haven't already seen this, you absolutely should. These guys are trying to solve the problem of service stubbing and service virtualization, not just for performance testing, but also for system testing as well. It's a really cool tool. Good friends of mine, their office is around the corner from ours. We're helping them to figure out how they do the latency simulation. Like if you're doing a performance test against a backend system, you want it to have accurate latencies as well, so your system gets the right behavior. Laptops are not load generators, said that already. Less is not more. Don't under-provision. Like you're wasting time by saying, oh, we'll just use a T2 micro in Amazon Web Services because that will definitely be enough. This is the time to get a C48 XL or 5 of them and just generate all the load. If you're in doubt, make sure you over-provision. There's nothing worse than, like I say, running a test for 10 or 12 hours and then finding out the only reason you didn't get the results is because your load generator was under-provisioned. And it also helps to make sure you've got memory usage and CPU usage and all those metrics from the load generators as well. A basic sanity check is, was my load generator saturated? Because if so, you need to keep going. You need to keep generating more load for your system. If you're instrumenting, basically read this book by Brendan Gregg, Systems Performance. He has a little cheat sheet table I've repeated here about what kinds of things are useful to instrument. This basic framework of utilization, saturation, and errors help you understand how is the system being used, what resources are saturated, and are there any things wrong with it. That's his table. I'll just leave it there for reference. I'm going to come back to this in a minute because it's easy to see in GitHub. But when you're running, how do you do it? What happens? So you do this. You do a warm-up process. Then you run with 10 users, 20 users, 30 users. Then you see is the system saturated. If so, you move to the analysis phase. If not, you increase X by some value and keep going. This arrow really should point to here. Actually, it helps to warm up again after each increment, but it'll probably be warm enough as it is. And what you're trying to do is to see how does this system behave after 10, 20, 40, 60, whatever many users. And what you'll end up with is some data. You'll have some latency distribution of 10 virtual users, 20 virtual users, 100 virtual users, and then you need to analyze it. And it's actually not that hard. I'm making it out like it's this dark art. It really isn't. The super low-tech way of doing it is to check the results by hand, and that actually does work. It's really handy. You can just plot a table and go from there. Probably the best way, though, is to turn that into a graphical representation, then try and figure out, like, what does that data tell you about the future of your system? So I did a whole host of tests against our website. I went from 10 virtual users all the way up to 200, I think. And I got all this data, and you can kind of see, like, eyeballing it is fine. I got some throughput numbers, and it kind of gets up to about 52 requests per second here when it's got 120 concurrent customers. Latency is, that's just a runtime. So that's kind of like what the throughput looks like. But what I'm more interested in figuring out is, like, is it saturated? And we're doing this is to figure out, like, if I plot throughput against the load level, I'm sorry for the green, it was much better last time I presented it. You can see at around about 110, 120, performance starts to go down. So already we can see that 110 concurrent users is around about our saturation point. We can go no further. To get better results, though, than just that simple visualization, it helps to fit some kind of curve to that data and figure out what it says. For those of you who aren't familiar, this is the universal scalability law. It looks complicated, but it's actually kind of simple. It just simply tells you, given a certain amount of offered load, what's the relative capacity that offered load can handle. And in an ideal world, this would be linear. But we have contention overhead, which is that kind of asymptotic plateau that you see in the graph. And we also have crosstalk overhead, which is quadratic in the number of users present in the system, and that leads to that retrograde performance. Every system has these pretty much in some form or another. Determining how big the contention is and how big the crosstalk is beforehand is essentially impossible. So you need to measure some data, and then you can fit this line. So when I fit that to my data, what I get is this cool little curve that says, it sort of flattens out about here, and then things start to get worse. It's just a prediction. If I take the derivative of that curve and find it when it just tips over from being positive to negative, I found out that it's about 124 concurrent users, I think, was the saturation point for this system. All of the code for this is on my GitHub, so feel free to browse. And this is sort of shown out in the table as well. If we look at the retrograde scaling, we see here that 52 at 120 customers, 48 requests at 130. So you can kind of figure that out from there. That process of just figuring out the saturation point is just giving you the data. Now you need to do the extra part of figuring out what does that mean, how does that perform at those different saturation levels, and you can choose a couple of different points on this to look at. So I think we have around about 50 concurrent users at our peak, and 120 is our, let's say our max. So those are two interesting things I want to look at, like what's my quality of service at saturation, and what's my quality of service at current usage levels. So now we're going to get into analyzing this data. I always say step 0 is learn to use R programming language, because I'm an R snob. Python's fine, suppose, if you don't want to learn R, which you should. Exploratory analysis, start there. Just make some plots, make some tables. It's super easy, and I'll show you some examples. From those, you'll almost certainly be able to answer your questions immediately. You don't need to do anything fancy. There's too much fancy stuff going on. Basic plots, basic tables really help. And it helps to link this to production data, and I can talk about that in a second. And you need to try all different kinds of plots for your data, because certain data is not great for plotting. Like the problem we had was that the maximum was like way out here, but most of the requests were here. So a histogram isn't particularly good. This is latency along the bottom and count along the Y here. I changed it into a log scale histogram. It's still not much better, but it does show there are sort of two peaks. I think these were ones where the pages were cached, and these were ones where they weren't. We managed to determine that. But that's not a great visualization either. You can sort of facet it out by the different page types, but they still have the same problem. So this is like what the home page looks like and the jobs page. You just need to keep trying all these visualizations. Time series is really useful because this is kind of what I expected it to look like. Most of the requests look pretty good, and these were big peaks. I didn't have the time to do the plot, but I have seen the results. If you overlay this with when big GC happened, then the GC was responsible for those pauses. So we know we need to tune the GC for our website to make it go faster. But actually, in the end, for this system, the best visualization was to use the table. So I just segmented it down by the different request types, then plotted the average latency, so the median latency, the 90th, the 95th, the 99th, the 99.9th. And I did this at the saturation point here, but you can do it at all the different points. It tells you some interesting stuff, like look how different the max is from the 99.9th. Like 1.5 seconds isn't too bad, but 5.5 seconds is crazy. But it's almost double from the 99th to the 99.9th as well. Really interesting stuff you can find out about your system. If you do it per load level, we sort of see what happens. This is where saturation becomes a business metric as well. Like, it's one thing to say performance gets worse at 120 customers, but actually you might also say, well, I'm not happy with some of these performance numbers. Here it was okay. It went from 1.5 seconds at 99.9 to 6 seconds at 130. If I'd kept making more requests, actually, I could have made that arbitrarily large. That's kind of the essence of saturation, is once it's saturated, you can make the latency arbitrarily large. There's more of these examples in the slides. It helps to experiment with these different visualizations, because otherwise you're not going to understand your data. And you want to understand it in the context of your production metrics as well. So we just did this for a customer. And we did all these optimizations, we did all this testing and so forth. But when we put the optimized settings into production, we did some measurements in production as well. And we saw that the optimization had reduced their 95th percentile latency by over 50%. And that's the critical thing, is all this testing in test environments is great, but measure it in production as well. I want to take a minute to summarize. Do these tests with a purpose. Please check out the code for this on GitHub, and you'll see what I did. It's fairly self-explanatory. All of the effort went into thinking about the design, not into writing the code. It's like super simple stuff. It's a bit of groovy code. Test with real user models. If you're not doing that, everything else is pointless. If you don't have that right now, you may as well just stop load testing, because the numbers you're getting are at best wrong, and at worst, like dangerously inaccurate. Like they're giving you wrong conclusions about your system. That load curve exploration tells you so much about your system. If you're just testing at one load level, what's the point? Like, understand how the system behaves at different amounts of load with different customers on. And then think about that in the context of real data. What does this mean for conversion? What does this mean for bounce rates? So on and so forth. But the most important thing you should take away from this talk is that performance matters. It's real money. It's not just something we do for best practice or because we think we should. It's real money for your business, or real conversion, or real user retention. It really matters. Thank you very much.